So I'm not going to ask you to memorize the history, but in discussing science, it's good to remember the name of the scientist, okay? The experiment, as well as the observation. Because from there, you lead to conclusion or inference, okay? Okay, so we should appreciate their work, the scientists' work, because nowadays that we actually get the results from their experiment, from their hard work, from their theory. So today is what we get. And today, the technology, the one that we use, are based on their hard work and all the. It was not really, a happy life. Scientists does not have a happy life or whatsoever, but this is at least after some centuries, we appreciate them by remembering and actually learn about them, how they conduct experiment, what are the observation, and what are the conclusion. So I did give some example. J.J. Thomson start from uh, plum and pudding, uh, plum and pudding theory, but then okay, this is by Dalton, okay, and then right, J.J. Thomson start with plum and pudding atomic model, but at least he understood that there are charges particle in atoms. It does not name the charged particle in atom as electron, but they know there is a charged particle in the atom, and then Millikan identified the charge of electron being negative, and then Rutherford proposed that all positive charge are concentrated in a central core called nucleus, the observation of nucleus. So these are all the experiments. The first one by J.J. Thomson, where he observed the uh, charged particles, okay, but he does not name that charged particles yet, but he observed there is positive charge and there is also negative charged particles. And then Millikan identified the negative charge of the electron, and Rutherford identified there is a dense positive charge in the middle based on his observation of gold foil experiment. Okay, so those are examples of, right, those are examples of history of atomic model. Okay, it looks, it is not like you think that it is not important, but actually it is very important. Okay, but it's not going to be in your final exam question. So, right. The other one is we have discussed as well electromagnetic radiation, how the excitation of electron and how the relaxation of electron happen. Okay, so I hope that you remember, because that's the most important process in this topic. The excitation of electron and the relaxation of electron involve specific amount of energy absorbed as well as specific amount of energy emitted, and it is called photon, right? So we have discussed in detail the photon, okay, concept, and the quantized energy concept during our last discussion. So that's very important, very important for you to understand. I'm sure that all of you has come across those discussion before CHM3000, okay? Or I don't know, might be somewhere different topics, different subjects. So this is very important for you to understand the process of how the excitation of electron, okay, and the relaxation of the electron between different energy level known as orbital, okay, and the photon is emitted. The photon, right? And the photon is emitted, and the photon you can imagine like is a bucket of energy, right? Okay, so this week, as I have mentioned in the group, that we are going to discuss detail on photoelectric effect. So photoelectric effect, I think we have also watched this video together last week, and I'm going to show you the experiment. Okay, no worry, I'm going to share this latest slide with you after this. So this is what happened. This is what we call as photoelectric effect. So when the light is shown, okay, the photoelectric effect is a phenomenon which electrons are ejected, okay, from surface of a metal. Okay, so this metal will you can have different metal. When light is incident, is bombarded on the surface of the metal. So these ejected electrons are called photoelectrons. It's important that emission of photoelectrons, this one, and the kinetic energy of the ejected electron. So this ejected electron, they have their own kinetic energy, yeah, of the ejected photoelectron is dependent on the frequency of the light. Frequency means that, of course, it is related to lambda, it is related to the energy of the incident light, okay? So we know that the concept of quantized energy is quantized. So by now you should know that this energy is very specific. The process through which photoelectrons are ejected from the surface of the metal due to the action of light is commonly known as photoemission. Okay, I think this is the process of how the electron is being ejected out. Okay, so you can also, when I share with you this latest slide, okay, you can also look at this detailed explanation on photoelectric effect. Okay. And then you can look at the detailed explanation if you wish to in this link. Yeah. So when we talk about experiment, okay, it is important to, of course, just like the history of atomic model, we talk about the experiment, so we have to talk about the observation as well as the conclusion. Okay. So if you look at the picture just now, okay, incident light is shown on the metal surface, and then photoelectron is ejected. Okay, so there is existence of threshold frequency of the incident light. Means that for a given metal, okay, so for a specific type of metal, no photoelectrons are emitted if the frequency means that the energy of the incident light is lower than a certain amount. I think I have discussed that is the concept of quantization of energy. So if the lights below the threshold, no photoelectrons can be emitted. No matter, okay, as I mentioned in the last discussion, even if you show the lights for 24 hours, 48 hours, if it is not above the threshold frequency, then no photoelectron will be ejected. So that is the observation of photoelectric effect. Emission is instant, means that if you have enough energy, okay, if you have enough energy, the photoelectrons will be instantly ejected. Okay, the electron will be even though the light is just shown, you just shown in a very short time, you just bombard the lights on the surface of the metal in a very short time. Okay, the electron can be ejected provided it has the value of above threshold frequency. So it does not need time. It is instantly, can occur instantly. Okay, instantaneous. Okay, emission of photoelectron takes place almost instantaneously after the light shines on the metal, with no time delay. Means that it is a instant process. It does not depend on the intensity of the incident. Means that you don't have to like take time, bombard the light, and then the electron is ejected. Once, if it is enough in energy, then the electron will be start to eject. Okay, and what about the kinetic energy of the photoelectron? Again, is independent of intensity of the incident. Okay, it is always dependent with the frequency as well as the energy. Okay, so it is not dependent on intensity, means that how much you show the light, but is the frequency of the light. Photoelectrons emitted from metal have a range of velocities. Okay, depend linearly on the frequency. Okay, this is what I mentioned before. Right, so this is the concept of work function, which I mentioned in the group yesterday. Okay, so this is the formula of work function. Okay, anyone has come across this formula? Anyone? Have you
Yes, bro.
discussed? Yes, also. Oh, everything. So I think this is what you the most important. I think this one you are very familiar with. Okay, but specifically for photoelectric effect, there is what we call as parameter of work function. Not just like the Einstein equation before. So specifically, the work function is related to this issue, okay? Because in order for the electron to be ejected out, okay, there is a resistance. I call it a resistance, okay? In order for the electron to go out from the original position, okay, it has to like go through electrostatic, okay, some resistance from the location of the electron. So this will result in some energy loss. Okay. So this is expressed in a form of work function. Why suddenly? Okay. It is expressed in a form of work function. So this work function actually is very specific to a different metal. Means that you have different metal, you have different work function. Okay, so it's not that difficult if you come across the questions. If you are to calculate the kinetic energy of the electron, you just need to know the work function. And you need to know the photon energy of the incident light. Okay, so that's how we calculate the kinetic energy of the electron, the energy of the bombarded or the incident light, and the work function. The most energetic electrons emitted will be those very close to the surface, and they will leave the cathode with kinetic energy. Right. Okay. So that is photoelectric effect. So I'm telling you that this is very important. So these are tips for final exam. Okay, so when I stress something, you should spend time reading as well as doing this calculation related to kinetic energy of the electron. Okay, so this formula is important. Yeah. All right. Now the next one. Okay. I don't know how to use this. Always. Okay. The next one. Okay. So we have covered all this. Right. Okay. So the last, I'm sure that you have come across the Bohr theory, okay, in CHM3000. Okay, so can someone or anyone, okay, I hope it's not the same one, explain Bohr theory to everybody here? Whatever that you remember on Bohr theory. A Bohr atomic model. Anyone?
Basically, Morse are trying to explain the structure of the atoms
Okay.
and the behavior of electron within them.
Okay, all right. You are, I cannot find your name. Muhammad.
Ayman.
Okay, Aiman. Okay, thank you, Aiman. So, all right. So, Aiman said that Bohr model is the Bohr theory is explanation on the atomic model. All right, and the arrangement of electron. Okay, can I have like Fatin or Amira? Okay, what kind of arrangement of electron in Bohr model? Fatin, can you speak up? Hello? Is Fatin around? Yeah, can you explain to us when we talk about Bohr model, what kind of model of electron, arrangement of electron? Anything that you remember? Are you able to answer or you have difficulty to speak up? Mm.
Nucleus at the center and the electron on in the orbit.
Okay, in the orbit. Where's the orbit?
Around the nucleus. And the orbit have its energy.
Okay, of course, the orbit has energy. Okay, so thank you. Siapa tadi ya? It's okay. Thank you so much. All right. Okay, so I think the easiest way to describe Bohr's model of atom is the electron is circling the nucleus, just like the planet is circling the sun. Yeah, so that is the idea of what Bohr talking about. And you mentioned about the orbit. Yes, okay, the electron is moving in a specific path. In a specific path, just like planets like Earth, Pluto, and all other planets revolving around the sun in a specific path. Yeah, if they don't use the same path, okay, and if the planets decided that you can just walk around like you wished to walk around the sun, then of course we have a collision long time ago. So electron follows specific path, okay, around the nucleus, and this specific path has specific amount of energy, this one. And this energy level is quantized. Again, it is quantized. And it is called, as you already knew, as orbital. Okay, so that is the idea of Bohr. Okay, the atom has a number of definite discrete energy level or orbits in which an electron may exist without emitting or absorbing EM radiation. Means that the electron can stay there, can stay at its position, means the electron can be here, okay, without releasing or absorbing energy, right? Provided the electron can maintain its own energy level. For example, electron 1 situated at orbital n equal to 1, then the energy should be the energy of the electron should have the same energy that is required to be in orbital n equal to 1. So E2, electron 2, because it is situated in n equal to 2, for example. Sorry, this is n equal to 1. This is n equal to 2. All right, I change it. Okay, so the electron 1, the electron 2, if it is in a location of n equal to 2, then the energy must be suitable for n equal to 2. So unless there is no change of energy, that you can stay there, but if the electron have change in energy, then it can no longer stays at the same location. Okay, so this is the idea of Bohr. Okay, that the electron, the energy of the electron is quantized, certain values. All right. So the other one about Bohr model, okay, also is the Bohr's equation. So have you done a calculation using Bohr's equation? Right. Okay. So I hope that by now you should know that you also have Rydberg equation, right? You have come across Rydberg equation. Where is it? Okay. Rydberg equation is here. Okay. So this is, I don't know why, I think there's something happened to my slides. Okay. But I think I have shared with you the PDF. So I don't know whether it has the same problem. Okay, so Rydberg equation. Okay, it's okay. Next week we're gonna do some example just to revise on the Rydberg equation. Okay, so Rydberg equation is calculating the wavelength on the based on the energy changes. Okay, and we can also use what we call as Bohr's equation. Okay, to calculate the energy of the orbital. Right. So this one, Bohr's equation as well, we are going to discuss next week on Monday. All calculations will be discussed next week, because I prefer to have physical class to show the calculation. So now the last part of Bohr's model is the problem. Okay, so not all, of course, all theories have some issues. So what is the problem with Bohr model? It can only explain a single electron system. Means that it can only explain, of course, hydrogen atom, because hydrogen atom has one electron, or any other single electron system. Okay, means that for example, K plus, sodium plus, okay, they are all one electron system, okay, single electron system. So this can be explained by using Bohr's model. Okay. Okay, so everybody is okay around for Bohr's equation, for Bohr's model. Okay, we have come to this learning objective. Okay, so for relating Bohr's equation with Rydberg equation, actually you can this is not important for for final exam, but then if you wish to know, we can derive Bohr's, we can relate Bohr's equation with Rydberg equation, and you can refer to any textbook in general chemistry. They actually have this. You can just Google how to relate Bohr's equation with Rydberg equation. Okay, and I'm telling you, Bohr's equation is important for final exam. Okay, so calculation wise, focused on Bohr's equation as well as work function equation just now on the kinetic energy. All right, so let's move to the last part for today, is wave particle wave duality properties of electron. Okay, so for that I have to move to a bit far because we're not going to do electron configuration. So I think you have done that before, and it is not covered in this CHM3101 topics. So I'm going to skip the electron configuration. So let's move to Heisenberg uncertainty principle. Okay, so can someone explain what you know already about Heisenberg uncertainty principle? Anyone? Or I have to mention names? Nur Fatia, are you there? Nur Fatia Muhammad Muzamil. What do you understand about this Heisenberg uncertainty principle?
Yes, Prof.
Uh-huh. So what do you understand? In your own words, what do you understand Heisenberg's uncertainty principle?
It's about momentum.
Momentum of what? Electron, right?
Yeah, electron.
Yeah, we are talking about electron. Okay. So what does Heisenberg point out about the electron? Yeah, it's okay. Whatever that you understand, whatever that you remember from the previous subject that you have taken, right? Nur Amira Azlin.
Yeah.
Anything that you remember? It's okay.
Good job.
Anyone?
Pasal
It's
apa
okay.
tu?
Sorry?
Maksud Prof tadi pasal apa? Remember pasal Heisenberg tu ke?
Yeah, yes. What do you understand about Heisenberg uncertainty principle? Your friend mentioned about momentum of electron. So what is it about? Tak apa. Whatever that you can remember from your previous subject before. Okay, anyone can give your view on this matter? It's okay if you can answer. Yeah.
We cannot know the position and state of particle of electron.
We were talking specifically for electron. So we cannot identify, okay, it is stated in the the first statement here, okay. It is impossible. I don't know at this moment whether it's still impossible or not. But at this, according to Heisenberg uncertainty principle, that is impossible to measure with complete precision. Yeah? Complete means that you can pinpoint the exact coordinates of the electron. The velocity, okay, you can also mention momentum and position of a particle simultaneously means that you can know the momentum, the velocity, and the position, the location, the coordinate of the electron. Okay, so what does it mean? Okay, I think I mentioned during our last discussion. Okay, if it is for normal objects like a ball, like we human, big objects, okay, this is not important because you actually can have a look at the location, exactly where is it, where the ball is, where that particular object is. But for small particles like electrons, small particles like electron, this is not possible. Okay, this is not possible, right? You cannot like know the momentum as well as the position of the electron specifically where. Okay, before this we discussed about the Bohr theory, right? Okay, so we know that this is nucleus and this is electron. So based on that, we know the electron should be at specific orbital. Okay, but according to Heisenberg, okay, according to Heisenberg, what we only can pinpoint or know is only the probability. Okay. Okay, we can only know the probability of finding the electron. So you can see electron is not exactly in one line, just like what Bohr's theory talking about. You look at this, it's not exactly in one line, it's actually in a form of clouds, in a form of electron clouds. Okay, so you can see from the graph, okay, as the distance from the nucleus means moving this sideway, you can see the distance, as the distance increase from the nucleus, you can see the probability of finding electron is getting low. Yeah, you can see the curve is moving downwards, right? So this is according to Heisenberg uncertainty principle. So the electron is not actually in a single line like we imagine, but it's actually on the in the form of clouds. Okay, and the density of the electron the probability of finding electrons will be different according to the distance from the nucleus. So it is far away from the nucleus, then finding the electron, probability of finding electron is getting reduced. The number of electrons, the number of probability finding electron is getting reduced. So this is what Heisenberg's talking about. And this electron density comes within variations in the shape, size, and orientation. So that is why we have the s orbital, p orbital, d orbital, and so on. Yeah, there are others as well, g. Okay, so we know that this has different shape. For example, s is circular. Okay, p is dumbbell, and so on. So these are the shapes of the orbital, and you can also have orientations of the orbital. Means you can see is y, x, z. So this is called orientations. So this is where the probability of finding electron is, okay, according to the orbital concept. Okay, so it starts from Heisenberg's. Yeah? Okay, so you can see, I hope that you can see the evolution of from, that's why history of atomic model is very important for you to see the evolution. Where is it? For you to see from the simplest idea of atom, moving on to a bit more complex, the idea of nucleus, the idea of electron, and then Bohr introduced the idea of orbital. But in the towards the end, the model or the idea of orbital also become more complicated, related to size, related to shapes, orientations. That is the idea when we start to discuss S, P, D, and F. And then I think you also know that the orbital also has magnetic, which is N, L, ML, and MS, right? The magnetic spin number as well, and then the orientation ML. So those are the based on the Heisenberg uncertainty principle. And the last part, okay, this we have come across this, we have discussed this, and I hope that by now you are familiar with de Broglie equation. So I don't have to discuss de Broglie equation, okay? But I will show you, so you can remember at least the de Broglie equation. Nope. I think I saw it just now. Yeah. So I don't know what happened to my slides. Okay. So this is the Broglie equation. So it's okay. So this is something you have done before, the Broglie equations, and it is very easy and very simple equation. All right. But what does de Broglie talk about? The equation is fine, okay? Let me de Broglie. Wavelength. Lambda. Okay. Sorry, I don't remember actually. Okay. So it's lambda. But what does de Broglie point out in his equation? What do you remember? What did you discuss on de Broglie equation before? Anyone? Arif Aiman? Arif Aiman, do you remember?
Already forget. Wait, I check my notes.
Okay. We have Aina dan Sarah.
Yes, Prof.
What do you remember about de Broglie apart from the equation?
Multiplication equation.
Equation to the equation is there. It's lambda equal to h Planck constant divided by mass and velocity. V is velocity. Yeah. All right. This is de Broglie. All right. And then what is the idea behind this equation?
Idea of that.
Yeah. Actually, I put.
Can I try, Prof?
Yeah. Yes. Sure.
Uh, I think the Broglie tried to describe electron have wave-like characteristic.
Yes. Okay. So de Broglie start to bring the idea of particles. Okay, not just electron. That particles has both. Yeah, wave and particle characteristic. So same goes to electron. Okay, so before this, if we talk about photoelectric effect, okay, it is always about particle characteristic. It's not about wave characteristic. Okay, so once the Broglie talks about his equation, he combined, because if you look at the equation just now, lambda equal to h Planck constant over mass times velocity. So he start to combine lambda, which is the characteristic of wave, right? Because it is wavelength. It is wavelength. So he start to combine the characteristic of wave with m. M is mass. Mass is characteristic of particle. So this is the beginning of combination or explaining that particles like electron can behave like as wave, as also as particle. It has both characteristic of wave and particles. So that leads to, which I don't put here, Schrodinger equation. So this is something that we are going to discuss next week on Monday. We are going to discuss, of course, calculation on Bohr's equation. Bohr's equation. I don't know whether Rydberg is something that, but I can do. We can do some revision on that. So Schrodinger Schrodinger equation. Yeah. Right. So these are the three things that we are going to discuss next week on Monday, hopefully. And I hope by now you have understood the evolution from history of atomic model, the very simple model until we have some complicated ideas. And the last part that I would like you to study before we end this class is for you to look on the idea of particle wave duality of electron. Okay. And please look at what we call as double slit experiment. Okay, because in science, everything has to be evidence. Okay, so the evidence among the experiment that is answering the explaining the particle wave duality of electron is double slit experiment. So I hope that you can browse through what is double slit experiment. And next Monday, we are going to do a calculation example of Bohr's equation, probably Rydberg equation, and we are going to discuss Schrödinger equation. All right, okay, that's it for today. Any questions?